A breadboard is divided into three main sections. The first section consists of the power rails on both sides. These rails are used for power distribution, and all points along each rail are connected horizontally. The central area contains terminal strips, where components are placed. In this region, each vertical group of 5 holes is electrically connected, but adjacent groups are not connected to each other. The center gap separates the left and right sides of the board. This gap is used for placing integrated circuits, and there is no electrical connection across it. In our kit, we include an ESP32 microcontroller, which is a powerful and widely used platform for IoT and embedded systems development. The ESP32 microcontroller should be carefully removed from its packaging to avoid any physical damage or electrostatic discharge, ESD. Before handling the module, it is important to discharge any static electricity from your body, as ESD can damage sensitive electronic components. This can be done by briefly touching a grounded metal object. After removing the ESP32 microcontroller, inspect the pins carefully to ensure they are straight, properly aligned, and free from any mechanical damage. The kit also includes a development board, which serves as the main interface for programming and connecting external components. This board should also be removed carefully from its packaging. Once both components are prepared, you are ready to proceed with the assembly and development process. Now we also have a DHT11 sensor, which measures temperature and humidity. We will open it as well in this package. When we begin the assembly process, we are working with an evaluation board. This board includes its own external power management system. It can provide both 3.3 volts and 5 volts outputs to the available pin headers. In this setup, the jumper is currently configured for 5 volts operation. The board can be powered in multiple ways, either through 2 USB connections or via an external power adapter. Before installation, it is important to carefully consider the correct power configuration and ensure everything is properly set for safe operation. When assembling the system, we use an evaluation board that includes its own external power management capability. This board can provide both 3.3 volts and 5 volts outputs for the accessible pin headers. In this setup, the jumper is currently configured for 5 volts. The board can be powered either through 2 USB connections or via an external adapter. Before installation, we must carefully align the ESP32 microcontroller module with the evaluation board. It is essential that the pins are perfectly matched. Pin-to-pin alignment must be correct on both sides. We must also ensure again that there is no static electricity on our hands to prevent damage to the components. To connect the module, we gently align the headers and press them together with even pressure. The pins should be fully aligned in parallel before applying force. A light and controlled pressure is enough for the connectors to lock into place. If there is any misalignment in the headers, it can usually be corrected carefully using a general-purpose tool such as a screwdriver, but this must be done gently to avoid damage. Once aligned correctly, all pins should match from one end to the other, ensuring a proper electrical connection. We have prepared everything, and we have connected our sensor. These jumper wires are usually female to female. One end connects to the sensor, and the other end connects to the board. We have 3 pins. Just make sure these wires are properly inserted into the ports. You need to pay attention so that each wire is connected to the correct corresponding pin on the other side. One side of the connector has metal contacts. Make sure they are facing downward and properly aligned. The pins should be parallel, neatly aligned, and fully inserted into the sensor. Make sure the tab is fully seated inside the sensor. Sometimes we use a screwdriver to gently secure the pins in place. Ensure everything is tightly connected and nothing is loose. On the sensor, there are 3 labeled pins indicating power, ground, and signal output. They are marked as VCC, GND, and out. We need to make sure each wire is connected to the correct corresponding pin. For typical ESP32 based projects, this setup should be connected to pin D4, GPIO 4. You need to pay attention. The output signal wire, usually the white wire, is connected to the signal pin. This is an important point. The sensor's output must be connected to D4, GPIO 4, on the ESP32. If you look closely, the sensor has 3 labeled pins. S, V, and G. S stands for signal, V stands for VCC, power, and G stands for ground. When making the connection, the white wire, signal wire, should go to the S pin, while the VCC and GND wires should be connected to their corresponding power and ground pins. The black wire represents ground, negative, and it should be connected to the GND pin. The gray wire represents the positive supply, VCC, and it should be connected to the V pin. Make sure each wire is connected correctly to its corresponding pin. Signal wire right pointing arrow S. Ground wire, black, right pointing arrow G. VCC wire, gray, right pointing arrow V. Now let's move on to the LEDs. We have different types of LEDs. For this project, we use 330 ohm resistors, although 220 ohm resistors can also work. However, 330 ohms is generally safer, especially for beginners, because it limits the current more effectively and helps protect the LED from damage. We are going to install 3 LED lights in different colors. Here we also have resistors, and I will separate 3 of them and place them here. As mentioned earlier, each LED has 2 legs. The longer leg is the anode, positive, and the shorter leg is the cathode, negative. You can also identify the polarity by looking inside the LED. The larger internal metal piece is the cathode, negative, and the smaller piece is the anode, positive. It is very important to connect the LED correctly, as polarity matters. Also, LEDs must always be used with a current limiting resistor to prevent excessive current and avoid damage to the component. Now we need jumper wires to connect everything. Next, we bring VCC and GND from the board to the breadboard. As a standard practice, use black wire for ground, GND, use red wire for VCC, power. This helps avoid confusion and keeps everything organized. On the breadboard, the side rails, power lines, are typically connected horizontally along each rail. The middle section is made up of terminal strips, where each group of 5 holes is connected vertically, and there is a split in the center that separates the left and right sides. So, make sure to connect VCC to the positive rail and GND to the negative rail. All connections are made using the breadboard layout, following a standard ESP32-based template. We cannot connect components like LEDs directly to the ESP32 or directly to a USB power supply. An LED should also never be connected directly without a current-limiting resistor, as this can cause excessive current flow and damage the component. A resistor is required to limit the current, protect the LED, and prevent damage to the circuit. So, we place a resistor in series with the LED and complete the connections using the breadboard. Now, we will connect everything step by step. Now we place the LEDs on the breadboard. The anode, longer leg, of the LED is inserted into one row of the breadboard. The cathode, shorter leg, is connected toward ground, GND. First, insert the anode into the breadboard and connect it in series with a resistor. The other end of the resistor will later be connected to a control pin from the ESP32. The cathode of the LED is connected directly to the ground rail. We repeat the same process for the second LED. We repeat the same process for the next LEDs. Make sure all pins are straight and properly aligned. Place each LED a little apart for easier wiring. Keep them in the same working area, rows, for consistency. For each LED, anode right pointing arrow, resistor right pointing arrow, ESP32 pin, through wiring, cathode right pointing arrow, ground. As you can see, power flows from the control pin right pointing arrow through the resistor right pointing arrow into the LED, anode, then it exits from the cathode right pointing arrow to ground. Important breadboard note: even if components look physically close, electrical connections depend on the internal layout. On the breadboard, holes in the same terminal strip group, typically 5 holes, are electrically connected. However, the center gap isolates the left and right sides, so there is no connection across it. So, a resistor leg and an LED leg are connected only if they are placed in the same connected row, terminal strip. Components placed on opposite sides of the center gap are not electrically connected. We will use 3 jumper wires, 1 for each LED. The wire colors can vary, but it is helpful to keep them consistent for easier identification. For example, you can use a blue wire for the blue LED. Key important point is this: each wire must be connected to the same terminal strip, row group, as the resistor that is connected to the LED's anode. On a breadboard, holes within the same connected group are electrically linked. So, the jumper wire shares the same connection point as the resistor, and from there it goes to the ESP32 GPIO pin. For this setup, we are using the following GPIO pins: GPIO 13, GPIO 14, and GPIO 27. Depending on the board, GPIO 24 may also be available, but typically GPIO 27 is used. Now we connect everything step by step. First wire, for example, blue, connects to GPIO 13. Second wire connects to GPIO 14. Third wire connects to GPIO 27. Make sure each wire goes to the correct connection point on the breadboard, where each row, terminal strip group, is linked to its corresponding LED resistor. So the signal flow is ESP32 GPIO pin right pointing arrow jumper wire right pointing arrow resistor right pointing arrow LED anode right pointing arrow LED cathode right pointing arrow ground. GND. Important note: even if components look physically close, they are only electrically connected if they share the same terminal strip group. Also, the center gap of the breadboard separates the left and right sides, so no connection passes across it. Now we will add two functions, factory reset and Wi-Fi reset. For this, we use two additional GPIO pins, GPIO 18 for factory reset and GPIO 19 for Wi-Fi reset. These pins will be used to trigger the reset actions. These are two reset functions, factory reset and Wi-Fi reset. Under normal operation, these GPIO pins should remain in a floating, unconnected state, unless otherwise specified by the firmware design. As shown, they are not connected by default. To trigger a reset, you briefly connect the corresponding pin, factory reset or Wi-Fi reset, to ground, GND. When this happens, the blue LED will start blinking, indicating that the reset process has been activated. After the action is completed, release the pin and return it to its normal unconnected state. Important: only connect these pins to GND when you want to perform a reset. Do not leave them connected permanently. This is a working example of the setup. If needed, you can further improve or customize it by adjusting the wiring or refining the layout. Now we can organize the wires to make the setup cleaner. You can gently bundle or route the jumper wires to keep them neat and manageable. Also, make sure the sensor does not accidentally touch the ground or other exposed parts of the circuit, as this could cause a short circuit and potentially damage the component. Always keep all connections properly isolated to ensure safe and reliable operation.